Hi guys, today we are going to learn a little bit about the electronics laboratory variable power supply. It's the one that most of us get for our business or our labs or hobby, the 30 volts 5 amperes. We can also analyze the circuit for the 30 volts 10 or 20 amperes with it. The video is made about how does the system work. In this case, we will be able to understand and be able to make fixings, repairings in the power supply, or for students in the first years of schooling, they will be able to develop, create their own homemade power supply for the first year final project. Now, let's jump into the business. Most power supplies alike, they have the power button, the output connectors for the positive, the negative, and probably the ground connection that is just placed there to place a kind of a, let's call virtual ground, because most of them is not connected to anything. We have the current control with the coarse and the fine, and the voltage control with the coarse and the fine too. Some power supplies will be blind without anything for reading, others they will have analog voltage and current reading or digital ones in 3 digits or even more in the current. The power supply we're going to analyze is the 30 volts 5 amperes, but also with the same diagram I found in internet, we can analyze general the 10 amperes and 20 amperes too for this kind of models. This is one of the most common diagrams you can find in internet, and it is the diagram that match most of those kind of power supplies we get from China and everywhere now. If we try to analyze the circuit, it's kind of hard, and the reason is because everything is messy. And then the first thing that pops out in our mind is, okay, I have the positive and I have the negative in the power supply. So this will be the negative and this will be the positive. And the point connected to nothing, the green one, is the ground. And it's a big mistake that everybody will make. Even myself will fall in the same mistake. Why? Because when we start thinking this is the positive, so whatever is going this way is positive voltage until the source, and this is the negative, and whatever goes this way is the negative until the source, and I keep in mind that this is the ground, I will find a big issue that this diagram has a ground right there, and it changed everything in the game. So if this is the ground, how come will be this one the positive? Or there is something wrong in the diagram, or there is something missing in my knowledge. And guys, you can always bet your money that is something missing in our knowledge. We have to learn more and think different to start doing things properly. This ground, if I analyze, is the ground for the control electronics system, the power supply that feeds the operational amplifiers. And this ground that doesn't look connected to this point is truly connected to that point. Once that I figured out that, I start to understand that this is the ground, the common point reference to any power supply I have in this, let's say, power supply again, or let's change the word power supply for system, and this, let's use the word power supply to understand what fits my system. So in this case, this is just my patient and this is my resources. I cannot see it as a power supply anymore. Then let's forget this is a ground. Let's keep in mind this is the common place, and let's start the game. When I start the game in that way, I have to focus myself in this source, in this power supply, because this is the one that will fit my operational amplifiers. So this is my reference voltage for the control of the voltage and the current in the circuit. It's kind of hard to understand when we watch it like that. So what I did all research, and things got more complicated, because if it was messy to understand the transistors there, I found the diagram for the 10 and 20 amperes power supply. Is exactly the same, but it has more transistors. So if I try to follow how they are connected, believe me guys, it's a twist in my mind. So it's not that easy. Because this is electronics, we do not work, we just enjoy with it. I make a drawing, I redraw all the schematic again. I'm making the drawing myself. I found out all the collectors in the transistors are connected together, all the bases are connected together. They are in serial with a resistor, that all the resistors are connected together. Each resistor from base emitter is connected in parallel to one to the other to a common point. Now it becomes easy. This is one power supply, plus 12 volts, minus 12 volts, a voltage division there, blah 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 blah, and still a big pie to try to bite in once and to digest everything on the way. So let's make the principle of any fight, any problem, any difficulty we get in life, the first thing you have to do is to divide it. So because I make the drawing, then it was easier to make the division of the blocks. Now it's easy to understand. This is the control power supply. This is an extra power supply for the 10-20 amperes to feed the extra transistors power. This is the source AC for the power transistors. This is the power supply for the power transistors. This is the current control. This is the voltage control, as you watch it. This is the output. This is optional to make a current reading in the 5 amperes unit. Is not in the 10 and 20. And those transistors, they are voltage comparators, and they will get the voltage level in the output. The reason is because this is let's say 30 volts 5 amperes. If I put 30 volts 5 amperes in the output, most of the power dissipates in the output. But if I put just 1 volt with the 5 amperes, most of the power will dissipate in the transistors, and that will be a lot of heat. In that case, what is going to happen is those voltage levels detectors, they will switch the relays and they will chop the voltage. I will not see any changing in the output, but here I will have less voltage, so will be less heat, less power dissipation. Remember, the power is equal to the voltage times the amperes. Amperes are going to be the same. I just chop the voltage and I get less power there. So that's the reason those relays here, up there, are switching the voltage outputs in the transformer. Now that I understood that, we can jump in the first analysis and try to figure out component by component how does it work, and each one of the values I should calculate and get the reading from. In reality, this is very easy to understand. There is a 12 volts voltage regulator here, and I have a plus minus voltage source with a common place there. So if I understand right, this is 12 volts, and the voltage regulator LM7812 will drop minimum 2 volts, if not more, between the input pin and the output pin. So that will give me from here to here 12 plus 2 volts is equal to 14. And if I remember right, a regular diode will drop between 0.65 to 0.7 volts per diode. In one semi-cycle, two diodes are going to be working at the same time. So in that case, is 0.07 plus 0.07 is 1.4. If I have 12 volts plus 2 volts minimum drop, if no more, plus 1.4, that will be 15.4 volts. If I get 15.4 volts here, from here to ground, that means, if you remember right, to make the conversion from voltage RMS to voltage peak, I have to multiply the voltage RMS times the square root of 2. In this case, because I'm doing reverse engineering, I'm going backwards, what I have to do is to divide my 15.4 by the square root of 2, and that will give me about 12 volts RMS. That means the voltage here should be 12 volts RMS, and because this is a symmetrical power supply, has a center tap, this is the plus voltage and this is the minus voltage, as we can see it here. That means here there are other 12 volts AC. So from pin 13 to 11 there are 24 volts RMS, and from pin 12 to either one of them is 12 volts RMS. So it was very easy to understand. Maybe the complex part could be this component here. Why? Because this is an adjustable zener, and the adjustable zener requires a formula. First, let's pay attention that there is one jumper from here to here, from the center to the cathode, and is open from the center to the anode. Okay, now from the 12 volts with a serial resistor or shunt resistor, I get 0 ohms here and infinite ohms there. Why did I say that? Because we need this knowledge to apply for the following formula. This is my formula, the shunt resistor, and this is 0 ohms and this is infinite because it's open in the circuit. So my formula says V out is equal to 1 plus R1 divided by R2 times the reference voltage. In this case, the reference voltage from here to here is 2.495 volts. So 0 ohms because it's a jump, infinite ohms because it's an open jumper, 0 ohms, infinite ohms is open. We will apply the formula. V out is equal to 1 plus 0 divided by infinite is equal to 0. 0 plus 1 is 1. 1 times the voltage reference. That means the output there is 2.495 volts. So we solve it, and there I know the output is 2.495 volts, and the difference, because this is 12 and this is ground, the difference will be 9.505 volts dropping in this resistor, the shunt resistors. This is our voltage reference, and we're going to use it for adjustments in the power supplies. In the other side, this is the ground with the center tap, and from the negative of the diodes, here are the anodes, I get the minus 12 volts. There is a serial resistor there, and if I place this zener, I get 12 volts and I drop here the 3 volts different if I do not place the zener will be around 15 minus 15 volts. This is important to know because some of the power supplies doesn't have the minus 12 volts regulation and they just leave it in 15. So don't get scared about it. In this other side, from the point of ground here and from the negative voltage, in that case minus 15 or minus 12, because I place the zener is minus 12, I will place a 6.2 volts zener. So if it is 12 here, there will be 5.8 voltage drop. That is the difference. 12 minus the voltage zener is equal to the difference voltage drop here. So if I place this connection, I will get as a reference here the minus 6 volts, and here I will keep the minus 12 volts. With these ones I'm going to feed the the operational amplifiers for the voltage and current control. So how healthy is it will always depend from this zener to keep that voltage, and our reference will always depend from the voltage reference or adjustable zener. Easy, guys. The formulas for the capacitors, we will see later the formula when we calculate the power ones, so will be easy to understand. In this case they are using 220 microfarads, and the capacitor always in the other side of the voltage regulator is about 10% of the main capacitor, but also it could be less or it could be more. It depends how much do we need. In this case, for the design, they use the same value of capacitor. Now let's jump to the next. Don't get scared, it's not the time to cry. First thing you have to do is forget about the blue ones. They are the formulas. We will analyze them on the way. Let's just focus in the drawing by the moment, okay? This is very easy to understand, guys. The first step will be, remember this is our output, our 30 volts, positive and or negative, is to connect the load. If we connect the load, we can close the circuit and we can understand how it's going to work. Now, we know it is 30 volts in the output, and for the 5 amperes we have a 5 amperes capacity. So 30 volts divided by 5 amperes, it gives me a 6 ohms load resistor. Now that I have my load, I can continue with the rest. We say it is 5 amperes for our calculation for our 5 amperes. So that means 5 amperes divides between those 3 resistors. Each resistor is 3.6. Each resistor is 0.36 ohms. That means the resistors in parallel, this is the formula, will give me an equivalent resistor of 1.2, all of them in parallel, if I apply the formula. So now that I have the 1.2, I can calculate the voltage drop in those resistors. The voltage drop in those resistors is 5 amperes times the equivalent resistor, that is 0.12. The voltage drop here is 600 millivolts, 0.6 volts. Easy to calculate. Now I know from here to here there are 30 volts plus 0.6 volts. those transistors, they are going to have a voltage drop too, and those transistors are connected to the power supply there. So how much is the voltage drop here? There is a rule we apply in electronics, and I will show you about it. When we take the AC current and we, with the bridge rectifier, make the pulse waves, because we take this negative and we put it there. So the next step we do is to add a capacitor, and that capacitor is going to refill that area. And when this capacitor refills this area, if you pay attention, the capacitor doesn't refill totally straight, leaves a ripple that is not refilling. That ripple could be even 15% of the voltage. Now, if there is a 15% of the voltage that is not regulated in the tab, to do not take any risk, I will go down with the transistors and I will chop all this voltage for other 15%. That means from the power supply, whatever was there in the voltage peak to peak, I will put in the load only 2/3 of that, in my case 30 volts, and 15% is no good there, and I will leave other 15% in the transistors, is other third. In other words, 2 15% is 30%. So if this one was 30 volts, I will leave there 15 volts, and that's this formula where it comes from. The voltage collector to emitter, the voltage drop, is equal to the voltage in the input times 15%. That is the inefficient of the ripple in the smooth capacitor, and I will add other 15% extra that I will leave in the transistor, so it's at 30% in the transistors, or 33% if you want to call it, and this is the 30% of that, of this. So in other words, if it is 30 volts, I will drop here 15 volts. Now 30 plus 15, that means here I have 45 volts. And because I have 45 volts, I can apply again the rule that says voltage RMS times square root of 2 is equal to voltage peak. In that case, I have the voltage peak, and because I have the voltage peak, I am able to go and calculate my voltage RMS. Is 45 volts divided by the square root of 2, and that will give me the voltage RMS. Easy. And if I have about 45 volts peak here, I can look for a value standard of 30 volts RMS in the transformer. So that's the maximum voltage I will get there as voltage AC. So far, if we analyze, we understood what is going on there. We apply this formula, we apply this other formula, we understood this formula, we understood this formula, that is the 0.6 volts drop there, and we got this formula too. So it's very easy to understand once that you make the diagram and you get the formulas. Now the smooth capacitor. We said we are going to give to this guy 15% of non-good voltage, what we call the capacitor ripple. Okay, so if it is 15%, I make the formula, the calculation of the smooth capacitor, that is here. Capacitor is equal to the E load. E load, remember, is the current, the 5 amperes or 10 or 20, depending what you are designing your power supply. I will stay with the 5. I don't need fire in my house. It's too much power for what I need. Then the formula is 2 times the frequency times the ripple voltage. The ripple voltage for me is 50% of the input voltage, and the input voltage has a 45 volts peak. Now I will get a capacitor about 4,400 microfarads. The next commercial value is 4,700 microfarads. Because I'm using 45 volts, I will go with the next upper level capacitor, that is 63 volts. And I already calculate my transformer, and I already calculate my capacitor. Remember, if you're going to work with 5 amperes, you need diodes for twice or more of the current. Keep it in mind. So you have to go upper of 7 amperes diodes, even to 10 amperes. This resistor here, what is this resistor about? When I turn off the power supply, this resistor, many people forget to add it in their designs, is to discharge the capacitor. So this resistor will totally discharge the capacitor in 5 taus. 1 tau is equal to the capacitance times resistance, and in 5 of them, the capacitor is totally discharged. So it will take about 24, 25 seconds to totally discharge the capacitor. Easy. Now that we understood that, we can go with the transistors. But I forgot to tell you something. If this capacitor is 4,700 microfarads, this capacitor in the output is 10% of it. So now I got the value of it. Also, many engineers, they place a 0.1 microfarad capacitor there to avoid the noise. And sometimes they do the same here. This diode is for reverse voltage protection in the power supply. So now we know the 3 components, what are those about. Do you see this resistor here in the output? Okay, if we place here a 470 microfarads capacitor at the output, this resistor does the same to discharge that capacitor. And we always do that in 1/5 of the time we do it there. That's the reason of the value. Now if we come back to the formula to discharge the resistor, that means 470 microfarads times 2.2 K times 5. And we are expecting to discharge that in 1/5, so it should be about 5 seconds to totally discharge the output capacitor. If there was 25 seconds. Got it? Now, let's concentrate in the transistors. Guys, when we speak about transistors, we think about control and the Q operation point between the collector and the emitter. And let me tell you the good news that it doesn't work here. Those transistors are working as a switch. Yep, as a switch. And the system is made to keep them always on. From the 12 volts through R10 through 2.4 volts voltage drop, I get the current I need through D11 for the base of Q1 to make a Darlington, with the base of Q2 to make a Darlington, through R13 10 ohms to make a Darlington, to the power transistors. If I make a deviation of that current from here to here with the operational amplifiers, the current will go in this way, looking for the shortest way to ground, and will not see the transistors anymore, and they are off. So this circuit, as it is right now, is for the transistors to always be on unless I deviate the current through the LED diodes in the power supply. Got it? Now, I am able to calculate that because if I have the HFE, that is the gain amplification ratio between base and emitter for those power transistors, they are between 20 and 70 times the collector emitter current is the base current. So if I have 5 amperes, I have to divide 5 amperes between 20 or 70 and divide it by 3 for each transistor, but at the end it's the same. And I will get the current in this resistor, the current maximum, the current minimum. So with the current and the resistor, with the current, I multiply the current times the 10 ohms and I get the voltage drop there. Very easy to calculate, guys. If I get the current here, the current in this other point is very alike, so I can calculate the voltage drop there. Got it? Very easy. Then transistors will always work in on and off, not with operation point in between. This is the current control circuit, and it's very easy to understand. We have here the 2.495 volts voltage reference, and we have one serial resistor as a shunt resistor, one adjustable resistor, and the knob of fine and coarse knobs in the power supply. An operational amplifier. These 12 volts through R10 through the zener are going this way to the base of the transistors. If the operational amplifier activates, will take away the current and will not go to the transistors, and transistors are going to be off, otherwise they are on. Here, guys, is one of the most important advice you will ever receive when you're working in electronics as a student making your projects. This is the operational amplifier 741, and this operational amplifier has an offset balance leads here, and generally you use a 10 kilo ohms variable resistor. Guys, be careful with this 10 kilo ohms variable resistor. It's made just to adjust a little bit in the center. If you take the knob and you twist it all to one side or all to the other side, you will burn the variable resistor. So do it just a little bit in the center and not in the sides. You are very lucky if you can see the smoke and you can smell it. If you didn't see the smoke and you didn't smell it, you will spend hours without understand what is going on, what is wrong with your circuit, because you burn your variable resistor and the system is not adjusting the balance and nothing works fine. So remember this knob for the 741 operational amplifier, just a little bit in the center, but don't ever go with the knob size to size with it. Got it? Now back to the circuit. This is our 3 resistors, 0.36 ohms, that we set at 5 amperes, it drops 0.6 volts. Those resistors, if we come back to the circuit, are the base emitter resistors. Okay? And we know base emitter resistor would always be about 0.7 volts when it is on. So this resistor will go from 0 to 0.6 in 0 to 0.5 amperes. Sorry, in 0 to 5 amperes. The sense resistors. Because this voltage is fixed, what I'm going to do is I will adjust my reference here, my ground level, to annulate the 0.7 volts. And once that I annulate that, adjusting a little bit here, I am able to sense from 0 to 0.6 volts in the operational amplifier. That's the reason I set here offset minus 7 volts at this point, not with the multimeter. Is the function of what it's doing is canceling these 0.7 volts. Got it? And the reason why it cancels it is because when I adjust the fine and the coarse knobs for current, I will drop from here to here 0.6 volts, and I will get 0.6 here or 0.6 there. Now the operational amplifier is able to get the output or to cancel the output as I wish it. If I have the voltage drop here in the maximum resistance, the maximum resistance is 6.8K plus 1K is 7.6K in 0.6 volts, and I am able to get the current. If I get the current, the voltage between the resistance gives me the current. Now with the current, I can multiply the current to this resistor, and I will know the voltage drop there. 2.495 minus the voltage there minus the voltage there leaves me the voltage that drops here. If I have the current, I divide this voltage drop by the current, and I will know exactly the value of the resistor I have to adjust at that point. So that's very easy. Now you know what to adjust there. Also, do not forget, for this operational amplifier, the voltage here is 12 and the voltage here is minus 6. So that means the balance between them is not a 6 volts voltage level. That's the reason I use this as a reference to annulate this resistor. To get to this point, it was all the complexity of the diagram. The reason was because if I analyze, this point goes to the negative, and the negative with respect to our positive ground in the other side truly give me an inverted power supply, an inverted battery, a minus voltage, and it's very complex to try to understand like that unless we use Wheaton bridge and we analyze. This is 30 volts, 0 to 30, so the voltage will reflect on the adjustment resistance fine and coarse. When they are 0 ohms will be 0 volts, and when they are maximum resistance will be 30 volts. Now with the formula, the voltage that reflects from 0 to 30 volts and the total resistor is equal to adding both resistors. 1K plus 1.8K is equal to 7.8, and if I have the maximum voltage and the maximum resistance, I can get the current there. Dividing 30 volts by 7.8 kilo ohms. If I have the current there, I can calculate the current here. The current is exactly the same. So this is equal to 30 volts plus 2.495 volts. If there are 30 volts drop here, I can multiply the current by the resistance here, and I will get the voltage drop there. So the difference of voltage missing to get 32.495 is the voltage there. If I multiply that voltage there by the current here, I will know to what to adjust this resistor. And I already solved the whole problem. Just extra knowledge. This resistor here and this capacitor here is made to create a delay. When the power supply turns on, nothing is working properly yet, so I create here a capacitor charging time, and that time is equal, remember, time is the resistor times the capacitor, and the total time is times 5,000. Got it? This other capacitor here is just a capacitor to eliminate feedback noise, and this capacitor here is a bypass capacitor to filter in the offset. Now you can go to the next step. Same situation for the other circuit. This capacitor here is a recommendation from the manufacturer of the chip to eliminate it's a bypass to eliminate the oscillation, and this is the bypass capacitor for the offset. With all the knowledge you have, you are able now to calculate those adjustment resistance and this offset balance. And let's talk about it. I leave you the value of the resistance for the test, so you can rewind the video and make the calculations yourself. In the case of the balance, you have to make sure to apply 6 ohms load to the power supply and remove the load, and the power supply should give you, in that case, a reading in the voltmeter of 30 volts or 0 volts, and at the same time it should give you in the amperemeter 5 amperes or 0 amperes. So that's the way you adjust this. First you have to adjust those guys with the formulas we already spoke about. Next one is to understand what happened here, because I saw it in Facebook. Sometimes guys, they place, guys, I get 45 volts in my power supply output no matter the knobs, how much I adjust, and a little bit of current. And do you know how to fix it? Yes, if you get 45 volts here, it should be impossible to get 45 volts there, because you are getting, remember, 15 volts drop here. The only way it will be possible is if there is a short circuit collector to emitter. If there is a short circuit collector to emitter, you will get a reflex of your 45 minus the diodes, 44 point something. You will get the reflex of your 40 plus volts in the output, no matter how much you adjust in the knobs. So that happens if the power transistors are collector to emitter in short. If one transistor is open, in that case you will get more current consumed, and more current consumed will be reflected in more voltage drop in R10. Easy to catch. Also, if it is open, here the current will change too. because the equivalent value of the resistor is not divided by 3, it's divided by 2. So there will be a changing voltage here if one of the transistors is open collector to emitter. Easy. If the voltage is not regulated and you can see the ripple in the output, your capacitor is about to die or is blown already. So it should be a straight line and you should not see the ripple there. If there is a ripple, your capacitor is gone. Something else you can appreciate there is when we get damage in the transistors, we get damage in other components on the way. So we must learn to make a kit of reparation, is to fix everything that gets involved in the stage in order to ensure the damage, the origin of the problem or a secondary consequence is not going to come back to affect anything of us. Guys, it was very easy. I recommend you play this video at least 2 times to be able to understand the questions for the test. The test is about to adjust the resistors and some troubleshooting. And if you want to make a homemade power supply, you can take your time, watch the video 4 or 5 times patiently because it's long and it's very distracting for some people, and you will be able to understand each one of the formulas we apply there. I hope the video will be worth it for you. Is how does the power supply works, how does it makes its function with the formulas, and now you are able to fix, repair your power supply or to create your own homemade power supply using this knowledge. Thanks by watching the video. Do not forget to like and subscribe. See you next time.